Hey, everybody, and welcome to our June 13th webinar. That's the formal way of saying howdy. Travis has got a really cool topic about using the Flipper Zero. This is a continuation of a previous webcast Travis did. I went through the slides beforehand, and it was like, man, this is really interesting. Of course, I'm biased. You know, he works with me, and I like him. So, so starting today, you know, for the next hour, Travis is going to talk about exploring the Flipper Zero. He's continuing from the previous one. Travis, I'm assuming that you're going to give like a little bit of a callback for anybody if they weren't on the other one, just to.
Yeah. We've got this little slide here. You know, the last time on Dragon Ball Z.
Good. I thought I remembered that in there, and then I started thinking, wait, let me not throw him under the bus and say he's going to do this.
No. We'll kind of do like a little callback and just kind of touch on that. But ultimately, all of these go on YouTube, so if you missed it, don't worry about it. You can always circle back to it. The whole point of this.
Wait. Let me just make sure I got the housekeeping done. Sorry, I threw it at you and didn't mean to throw it at you. After we're done, we'll stop recording. The recording will be available as soon as it's processed and stuff like that. And if you want a CPE certificate, just send an email to education@securideas.com at the end of this. So, Travis, man, have a great time. I'm going to shut off my camera and my microphone so I don't interrupt. And I look forward to hearing this.
All right, perfect. Thanks, Kevin. So, hi, my name is Travis Phillips. I'm a senior security consultant with Secure Ideas. We are on a continuation here for the Exploring the Flipper Zero as a hardware hacking tool. The Flipper Zero is an amazing tool. It's got a lot of capabilities for like RF, infrared, those sorts of things. I kind of touched on these over some of our previous talks that we did. The last one that I did was the first part of this hardware hacking, and I decided that I wanted to do this part. I was going to originally try to squeeze it in the last one, but I was like, there is way too much to cover here. So this one might not make a full hour, but it should be pretty close to it. But yeah, it's 2 points that I did not want to rush through while we were also covering the other things. So in the first talk, we covered using the Flipper Zero as a USB to UART bridge to interact with serial on embedded devices. We also covered using it as an SPI flash programmer, and I kind of showed how you could make a circuit board for it and be able to connect to it with test clips, read, write, dump, verify flash chips, and then using it to program as an AVR programmer, which would let you use AVR Dude to program chips that are from the Etmel family, or microchip as it is now, and read them as well. You could read the EEPROM and flash from them and do that. So, but I was also originally trying to target and cover DAP Link and SWD Probe applications that are on this, which allows us to interact with JTAG and SWD. These are two things that generally when I'm talking to people out in the community at conferences, professional groups, I find that these are two things that people know a little bit about and would love to learn more about. So I figured we'll take a little bit of time, and this is why I didn't want to rush it in the last one, to kind of cover what these are, what you can do with them, and then kind of circle back around to these applications that are on the Flipper that would allow us to interact with these and what we can do whenever we have these. So starting off with the JTAG and SWD. JTAG is the Joint Test Action Group. And this is kind of interesting. This was originally designed as a testing standard. It basically provided a pinout interface and a way that we can interact with the pins originally. So doing boundary scans, because as chips kind of progressed, we ended up starting getting things like ball grid array, which is where the pins to the chips are actually on the underside of the chip. So you would actually have like your fiberglass surface here for the PCB, the chip here, and then like 100 pins underneath it. And it's like, okay, you can't visually inspect that. You can't get a probe in there to test it unless you had your PCB where you ran out test points. There isn't really a way to test this per se. You can't use visual, you can't use probes. So what can you do? The JTAG interface provided a mechanism for being able to hook up to a standardized interface and be able to test things. So if two of those pins underneath it were shorted, we would actually be able to determine that. But it just provided a testing mechanism. But things kind of got bolted onto it from there, such as being able to actually have like a on-chip debugger and things like that. And it kind of got built on. And with that said, it's a useful interface for QAing, but it's also generally is just like in the software world. Any functionality a developer leaves in for debugging is usually useful to a hacker. So we absolutely, as hardware hackers, will want to look at and try to exploit that. The other one that we want to cover today is SWD, which is serial wire debug. It's very similar to JTAG, except it only uses 3 pins is what you'd have to hook up to. If you ignore the ground, you just have a clock and a data signal. And it allows us to do a lot of the same stuff that we can do with JTAG. So to not really dive too deep into JTAG, I highly recommend checking out EEV's blog on this one. It was titled, What is JTAG and Boundary Scanning? He does a phenomenal job outlining this, and it's about a 30-minute video by itself. And again, he is also just kind of like, this is kind of like a high-level overview, but he does a good job explaining the boundary scan, the flash controller, because you can use this for programming. You can use this for the debug controller. There's various little chips in there that are like that you can actually access through the JTAG interface. He also points out too that you can actually run a JTAG bus effectively and chain devices together. So the 5 pins that you have for your JTAG is you have a test data in, test data out, so data in, data out, a clock signal, and a mode select, and then a reset. And the way that you would do this if you wanted to chain these together is you'd have the mode select and the clock signal ran as a bus. So you just basically have a line, you can have multiple chips connected to that, and that's fine. Now for the data in and data out, you would have the data in go to your first device and then its out channel going to the next device's input, and then so on, so on, so on, and then back to you. The only problem with chaining devices like that is you then create a bottleneck. The slowest device is now the speed of the entire chain. So it's kind of that. And then there's the reset pin, which is oftentimes considered optional, but I find that you'll have a much better time if you actually connect to it. There's a lot of times that I've had various software kind of throw a hissy fit if it can't talk to the reset pin. So generally try to find that one and get connected to it. The next one that we had was like I was saying, you want to try to find these pins on a board. Generally, it's kind of the same mindset that we had with the UART. You kind of look for pinouts or test pins or anything like that and see if you can find it. But we have more pins that we're targeting here. So you want to try to do enumeration of that if you can. You know, you can always look at the chip, like the main MCU or any chips, and see if they provide JTAG pins, and try to see if you could trace them out. But there's other options here. So the first one that I normally like to use is the JTagulator. This is a tool that was developed by Joe Gran, and it's an amazing tool for doing JTAG discovery because it had input protection, logic shifters, and 24 channels. The only problem with that recommendation is that these aren't being made anymore. And you can still find some of these online, but usually at scalper prices. So I've been trying to experiment and see if there's other better alternatives to make recommendations for people that are trying to get into this. And I think personally, my favorite one is the second option here, which is the Raspberry Pi Pico. It's a $4 microcontroller, and then there is a application out there on GitHub called BlueTag, and this is a piece of firmware that you can install onto the Raspberry Pi Pico. So if you're not familiar with flashing these things, you just hold down the boot select button, plug it into the USB, and then keep it the boot select button held down. It'll show up like a flash drive. You just copy the U2F file over to it, and then that's it. It'll reboot and it'll come back up. And once it comes back up, you can now connect to it over USB like it's a serial device, and it'll give you a menu. And the menu will let you do JTAG or enumeration is one of them. So this image that we have here, I have a GIF. The GIF will show you the ground pins. There's a few of those. Those are the ones that have the square pads here in like 3, 8, 13, and 18. And then by default, the firmware kind of provides us with 9 channels. So 1, 2, so they kind of go in order. So 1 and 2, it would be 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are your enumeration channels. These channels can be used to connect to random pins, and the goal would be to let the scanner tool that's inside of this blue tag try to do a brute force discovery of seeing if they can determine a pinout in some sequence with those pins that would result in a JTAG interface. And if it can do that successfully, it will actually tell you, okay, channel 0, which would be that pin 1 here, is actually going to be your T clock signal and so forth. And it would explain to you the pinout. And then the other option is if you have an Arduino, there's a JTAG enum that was designed to be a replacement for the JTAGulator as well. It's very similar, but honestly, at this point, the Raspberry Pi Pico is pretty inexpensive compared to Arduinos now. So it's worth it. And like I said, again, the one pitfall that I've had in my testing experience with the Raspberry Pi Pico blue tag approach is if I did not connect to a test reset pin, I'd often have it fail to actually detect the rest of the interface. So it would actually just say, yeah, you're not connected to a JTAG interface, and it would fail on me. So I say try to go for more pins if you can and just let it go. So as an example here, we've got like, this is an Imagination CI, what was it, CI20 dev board, but it was a MIPS board that I purchased a long time ago to just kind of explore and play around with the MIPS interface. But it did have a eJTAG interface on it, and that would be the first pins that you see over here in the orange. So for example, let's say that we tried to brute force these. What we would do is we take that Raspberry Pi with that blue tag firmware on there, connect these up. Just remember the third pin here is the ground. So we've connected 1, 2, 3, 4, 5, because we already know the pinout. We can just use this to test it. We would connect those up to it, and then we could actually use the blue tag software to try to do a JTAG enumeration. So J is the command to tell it to run the JTAG enumeration. First attempt, you can see it did not find any devices. There is an option, which is -P, which is designed to toggle pulsing of the pins. By default, it's on. So if you try to run the scan first and it doesn't work, try turning that off and then rerun it again. And on the second attempt, we can see it actually did determine the pinout, and it showed channel 3, 2, 0, 1, 4, and that it kind of mapped out our pinout here. So data in was connected to our third data channel, out was to the second, first was a clock, mode select was the first one, and then the reset was on the fourth channel. So once you figured that out, you're good to go. You know what the pinout is. You can now, you've mapped out a JTAG interface, and we'll go over playing with that in a little bit here. But first, we're also going to look at the SWD because we have kind of a similar process here. And like I said, there's only 3 pins that you really need to be interested here. You need to find a ground, a clock signal, and then a data in out. So a data pin, a clock signal, and then ground. In the screenshot or the photograph that I have here, this is 2 different dev boards. One of them is the Raspberry Pi Pico itself, and then the other one's what's known as an STM32 blue pill dev board. But in both instances, right there at the end of the board, they've got a clock signal, the ground, data in, data out. The other one, the blue pill, offers a 3.3 volt as well. So you can actually use this to get power to it as well. But again, it's just our in, out, clock, ground. So these are pretty easy to find in these instances. But even if you don't find it, like it's not labeled like this, again, the BlueTag software does provide a S option in the menu that would attempt to enumerate that. You can connect up to 9 pins, let it run through. Takes a little bit of time, but when it's done, it'll actually explain to you the pinout here. And as you can see, once it's done, it explains data was on channel 0, clock was on channel 1. And when it was done, it also kind of dumped some information that it was able to get about the manufacturer code of the device that it was connected to. Okay, so that's the methods that you would use to find the pinouts for these interfaces. So how does the Flipper Zero interface with these? The Flipper Zero will interface with these through 2 applications. DAP Link, which will handle JTAG or SWD. And then there's another one that I like to use, which is called SWD Probe, which the first one, DAP Link, is intended for allowing the Flipper Zero to act as a USB to JTAG bridge. So what it does is it emulates the, it was ported basically from the OpenDAP, which provides you with a JTAG kind of like standardized programmer that it emulates. And what's cool about that is that there's a piece of software out there that's called OpenOCD, which is Open On-Chip Debugger. And this software can be used to interact with JTAG interfaces or UART interfaces or SWD interfaces. And the application that comes inside of the Flipper for DAP Link, whenever you do run that, there is a option that will let you actually see what the pinouts is for each of these protocols. So SWD, it'll tell you you need to hook up to pin 2 and 3 on the GPIOs that are on this device. JTAG, it'll give you a range, and UART, it'll give you a range. So, but you can see all of this within the application. I've kind of like that about a lot of these Flipper applications, is that they kind of just give you the pinout. It's built right into the application. So like we said before, we had just run through an enumeration of possible pinouts on the boards and found the pinouts. So with that information, you can actually now just say, oh, okay, well, since I know where the clock, mode select, data in, data out, and reset are, all I got to do is just wire it to the Flipper Zero now, and then we're good to go. Enter the OpenOCD software. The OpenOCD software, like I said, is software that you can use to interact with JTAG and stuff like that. And there's a lot that you can do with that. But before you can do anything with it, you have to kind of start OpenOCD, and there's really 2 parameters that you need to provide to it. You need to provide a config file that will explain to OpenOCD what programmer you're using. So for DAP Link, you're going to want to use the CMSIS-DAP config. That tells it that that's what this programmer is that we're using here. And then the second one that you need to provide to it is the target, which is the chipset that is on the target device that we're trying to interact with and debug. So in the case of this, we're targeting the blue pill dev board, which is an STM32 family chipset. So you would take note of where these are on your system. This screenshot is from a Kali Linux install. So there you go under user share, OpenOCD scripts, and then there's interfaces and targets underneath there. So that's kind of how that gets separated. But those do need to be provided to it with the -F switch, which is telling it the files that it's going to use for the config. So one for the interface, the programmer, which is the Flipper Zero DAP config, and then the STM32 config for the target device, which was the blue pill. And when you start it, you'll first just see it kind of dump a bunch of information out here to the screen. But what you're looking for are these parts that I've kind of boxed into as red here. You can see it shows listening on port 6666, port 4444, and port 3333. So the more interesting ports here, so TCL, that's tool command language. It's for scripting this sort of stuff. That one's not going to be as interesting to you as the other two are. So port 4444 is the Telnet connections. This is something that you can connect to, and it's a shell for OpenOCD that will allow you to start running commands. And there's a help menu and everything like that. And then the other option is the 3333, which is a GDB remote debugging server. So what can we do from here with that information? So like I said, GDB debugging server 3333 is actually a hardware level debugging session that you can run with GDB. Extremely useful for reverse engineering. So this actually, like on a STM32 Blue Pill, you would normally do like bare metal firmware development for that. This would enable us to be able to connect to it, and we can actually halt the processor at that point and then start inspecting the registers, start inspecting memory, and step through the code execution, set breakpoints. We're in control of the firmware that's running on that device now. So we have a full debugger attached to it. Super useful for reverse engineering, as well as troubleshooting. So if you're ever playing with these, you actually now have a means to debug your own code. The other one is, like I said, the open port on 4444. You just telnet to it or use netcat. But this provides you with that console, and there's a lot of commands that you can run. I forget this headset automatically turns off when I do not have audio. There we go. So anyways, port 444 will allow you to halt and resume execution of a target device that you're connected to as a JTAG interface. It can also allow you to query registers, reboot the device, but the last one is the most interesting. We can enumerate the flash banks on the device, read the flash banks, write them, erase them, whatever we want to do. So kind of an example of the 3333 GDB. So this is kind of my recommendation if you want to go this route is if you're on a Debian-based system such as Kali, you're going to want to install GDB multi-arch from the repos. This is basically a version of GDB that was built with, by default, your GDB has support for your x86 and your x64 Intel architectures. It matches your machine. This one provides you with a multi-architecture GDB that can understand different architectures. So the STM32 chip is an ARM-based chip, and we're trying to debug a raw ARM firmware image. So we would use that. So what you would do is you just start GDB. I provided the -Q switch here, which just kind of suppresses some of the version information. But once we're in there, we're going to say set architecture to ARM, so that way GDB switches to context and understands that we're not trying to debug something that's Intel based, it's an ARM based system. And then from there, we're going to say target extended remote localhost 3333. That was that port that OpenOCD opened for us. So we're telling it that we're connecting to a remote GDB server to debug a remote process, which would be the process that's running on the target dev board. And then at that point, it should come in, it should just immediately break, and then we can do whatever we want. So as you can see, I have run info registers, and we can see it dumped these registers here, but if you look at them, it's R0, R1, R2. These are ARM-based registers for the CPU. And then if I did X/5I, which is saying I would like to examine the next 5 instructions from an address, which is $PC. I'm telling it to reference a register. And in ARM, the PC register is the program counter. It's pretty much the ARM-based equivalent of, say, EIP or RIP in the Intel world. It's a register that stores a pointer to the current address that we're executing a command from. So yeah, with that said, we now have the ability to examine registers on here, control the code execution flow of the device, and debug it, inspect memory. We have full debugging. We can debug this thing now like it's a desktop application. So that's a pretty cool feature for reverse engineering firmware on remote devices. But like I said, there's the other one, which is the OpenOCD console. And you got the halt, resume, reset, which are just hardware level controls for halt is basically like makes the device act like it just hit a breakpoint. It will stop execution. So if we had like a little firmware image, and this is the one that I was using for a lot of the examples screenshots that I was getting on here, is the firmware was just a quick little like blink LED. If you run that halt command, it'll stop on whatever state it's at. So if it was off, it's just going to stay off. If it was on, it's just going to stay on. It's not going to do anything until I give it a resume or a reset. Resume would just allow it to start executing again. Reset will reset it, but that ultimately does unleash the halt that it was being held by. And like I said, one of the other interesting commands, and some of these commands can vary depending on what the target is. So in this case, we're dealing with an STM32 chipset. But most of the time, you'll end up with a flash section. So you'll end up with flash commands. The screenshot that I have here shows us connecting to it just using netcat. But you can see once we connect it to it, I can say flash banks. And what that does is that will tell you what banks are there for the flash. In this instance, with the STM32 chip that we have, there's only one bank. It's at, index 0, and it'll actually tell you where the address for that one is and the size of it, which is useful to know. You can also run help and then flash read. You can give it kind of like partial hints to what sort of command you're looking for. So if you ran help on an STM32 chip inside of OpenOCD, you're going to get a screen that's going to scroll for probably about 2 or 3 seconds, dumping out a list of commands. It's a very big help file. So this can actually help you narrow it down. Just be like, I only want to see things that are related to flash or reading. And with that, we ran that and we can see it actually just showed us flash read bank ID, which would be that 0, file name, which would be the file where we want to write this memory to on our local file system from the target device. So we're pulling data from the flash memory on the device and writing it out to like a .bin file on our system. And then we need to provide it the offset and the length. Those are optional arguments, but sometimes they can be worth it. So like an example of this would be this screenshot here. I could say flash read bank 0. That was the only one it had. And then I'm not going to provide it offset length or anything like that. I'm just going to say, dump this out to temp/test.bin. And it'll say, okay, cool. And then it'll tell you how many bytes it read and then tell you where it did that. And if we look at that now, I can actually do it with the LH. We can say we got a 32 byte or 32K file, 32 kilobyte. And we can see that this test.bin, we got 32 bytes. And this firmware was pretty small. This was just using an example of how to do a flash using just raw assembly. So it's a very small image, but you can see that that's there. OpenOCD also supports direct command execution. So if you didn't want to connect to the netcat session, you can actually use the -C switch to provide commands to it to execute. And you can actually change these. So we could actually do like -C init, -C reset halt, which will just clear the state, and then tell it to do -C flash read bank to firmware.bin, reset and exit, which would kind of put the device back to its normal state. But this would trigger us to be able to dump the firmware and get whatever was on it and then reset it back to normal like nothing happened. So, and if you do that, you'll just see it just dump out the information there. It shouldn't open up any of those debug interfaces. So the port for GDB should not be there and so forth. But this allows you to just chain command execution to run various OpenOCD commands. So in this case, the firmware that I got from that one, this is the dumped firmware that we got from the chained command. And then this on the right was the original .bin file I programmed it with. So Side-by-side hex dump, we can see they're exactly the same, except this one is bigger. And because the original file was only 436 bytes, it was a direct assembly file that built this. So very small, but we read the entire flash bank on this one, so we got more data. But you can see byte for byte, it's the same. So this actually did successfully allow us to recover a firmware image of this. And fun fact, since this was built in assembly with the PILBlink.bin here, you can also use OpenOCD to flash firmware to a device as well, because that was how I actually programmed it. So yeah, side by side, this is a mechanism that you can use to get a firmware off of a device. And like I said, we did this through a pinout with the JTAG interface or SWD interface. We didn't have to desolder a chip or anything like that. I think with some of these boards, like you might have to solder in pin headers from time to time, or solder wires down to maybe a test point that's on the PCB. But a lot of times you can get away without taking a chip off to get to the flash memory. So that was pretty cool, and that gives us a lot of ability to use the Flipper Zero from our laptop over to a device. There's a cool little program that you can also get for the Flipper Zero, but it's only for SWD. It's called SWD Probe, and this thing kind of lets you do a lot of the stuff that you could get away with OpenOCD without the laptop at OpenOCD. So, like I said, this is just for SWD, but one of the cool things about this app right out of the gate is if you just launch it, it'll tell you to connect the clock and data pin to any two pins on the GPIO thing, and it'll just automatically figure out what the pinout was for those two things. So it can actually automatically kind of do what BlueTag was doing there, where it figured out what the clock signal was and what the data signal was. So pretty cool by itself. So you can kind of cut not only OpenOCD out of the picture with that, but also BlueTag if you want it to. And that allows you to actually use this in the field when interacting with these devices, especially when you consider that SWD is very common with ARM-based devices. And on top of that, it's just two pins to connect to it. So it's definitely worthwhile to look into. But on top of that, it can extract information from there, let you kind of inspect some things, but they also have some scripting language here that allows you to run various things. So like I said, one of the tools that's in here is a memory dumper. And I told it to go approximately to where we saw the code for my firmware start in the firmware dump, as well as the original .bin file. And we can see that we're still seeing about the same thing here. We're seeing the same bytes that we had from the original firmware dump. So we can actually just explore that from the Flipper Zero if we want it to, as long as we can connect to an SWD interface on the device. But like I said, the other more interesting part is that there's scripting support. So we can actually build scripts that are designed like dump STM32. Since we know that this model of chip that we were dealing with before has one memory bank and it's a predictable size of internal flash, we can create a script that can actually dump that and then have it read that and just dump that to the SD card that we have on our Flipper Zero. So there was one there that came with the application that dumped STM32. I ran into a bit of an issue with it because the memory addresses were a little bit off for the spec that I had for the blue pill that I was working with, so we had to change it. Basically, the only line that needed to be changed really was my mem dump here. But the other problem that I kind of found with this one was there is a scripting interface for this thing, and it is not documented really well. So you do kind of have to go through the source code. If you look at the source code, you're mainly looking for the SWD Probe app.c. From there, you can actually find where it's exporting all these scripting language keywords and whatnot. But for memdump, I kind of figured it was memdump, and then the second argument is your file name where you want it to dump it, the address, the length, and then flags, which is from the comments that were in the code. It's supposed to mean 1 equals reading, continue reading even if it fails. to okay if it cannot fully dump. I don't remember it actually making use of that though, but that's what those were supposed to mean. But once I fix that script, I can actually connect this thing over to the Blue Pill dev board now. And then once I have it connected, just run the script and you'll actually see a dump status where it actually will tell you, you know, it's dumping and it's at 46%. And then when it's done, it'll just tell you that it's finished. And once that's done, you'll actually have the same firmware file on your Flipper Zero. And at that point, you can just take that, walk over to your computer, drop it onto there, and then you could fire it up in Ghidra or IDA Pro, whatever you want to use for reverse engineering efforts. And same thing, you could also potentially use this to write flash memory and reprogram something. So it's a pretty cool little application for that sort of purpose. Anyways, my thoughts on that is that my mind hasn't changed. This thing is still an awesome tool for hardware hacking. If you haven't checked it out yet, there's actually something really cool that came up with some of the more recent updates to the Flipper firmware. I've started using a firmware that's called the Momentum firmware, which has got some extra stuff here, but even the vanilla firmware has this now. But there is now a JavaScript API, which can actually allow you to write JavaScript files that can invoke some of the like underlying API calls that exist on the Flipper Zero for doing things like interacting with GPO or NFC, etc. And this makes it so that instead of having to write an application in C, you can actually just quickly throw together a script in JavaScript for various types of payloads. And I find this to be particularly useful because one of the things that in the Momentum firmware that we have access to is you can actually use the JavaScript to spin up a UART interface, which allows you to really quickly just create I need to execute a custom command on this UART interface. You can whip together a quick and dirty little application and then push it to this and then just run that JavaScript file. And it would actually set up the UART interface, allow you to send the command across, and then it just finishes. So that's definitely worthwhile to check out. So cons, I would say that, like I was pointing out, was that SWD Probe, the script documentation is not really there. I would love to see that get improved. The implementation of JTAG enumeration. So like I said, we had the JTAG, JTagulator, blue tag, and the JTAG enum for the Arduino. Those are three different tools that we can use for that. I think it might be possible for us to get that sort of functionality natively on the Flipper. I just not sure if anyone's taken a stab at it. So might be a project worth pursuing. And then same thing with the UART is, in my last presentation, I was kind of covering UART. Once you figure out the TX and RX pin, that's all that UART had, was it had the TX, RX, and ground, which is cool and all, except for we're missing a clock signal. And since we don't have a clock signal, the way that this is usually handled is a kind of a predetermined baud rate that just says that we operate at this speed. And you would have to kind of figure that out. And I covered some ways that you could do that, but it would be nice if this thing could potentially figure that out by just monitoring clock cycles, seeing the shortest time between a falling edge, rising edge, and just try to get an estimate for what the frequency would approximately be for the baud rate. So I think those are just some things there. But with that said, like I said, this probably wasn't going to be a full hour, so it's fine. But I wanted to go ahead and open the floor to see if anyone had any questions about it. So sounds like you recommend using the Blue Pill dev board for more reliable results. It's just a board that I had that I was using for teaching for a bit, primarily for dealing with SWD. I would say, actually, if you want to play with a board for development that's ARM-based, the Raspberry Pi Pico has actually been kind of a good one to use for that. The Raspberry Pi Pico actually has a pretty good SDK kit and multiple languages. Like I've seen people that have been programming these using the Arduino IDE. Example of this would be a project that's open source. It's called USB Valve. That one's being programmed inside of Arduino, but there's also people that are using Python, because there's a Python library that you can get that would actually allow you to program a Pico as Python, as well as just being able to do it in native C, which is an excellent approach as well. You just get it, download the SDK, and then you can actually start using it. So that's an option as well. So the Blue Pill versus the Raspberry Pi Pico, it doesn't really matter which way you go. It's just those are two options for dev boards, and they're both really inexpensive when you look at them online. Any other questions?
I have no questions. So from the last video about dumping SPI flash, Galen was running into problems dumping flash with the flipper, but did not run into problems with Raspberry Pi. Would we ever be able to order the flash dev board?
So I was not actually looking to make those in like any sort of production run. I'll check about seeing if I can actually just make that an open source board. It's not a complicated board. Basically, if you go to the help screen that's in there, it's just helps you with the wiring that you have there. The complicated thing about the wiring for that one was that, let me see if I can find that app real quick. Yeah, it's buried in menus a bit. Let's see. Okay, yeah, so if you launch the SPI app, it's that thing there. And it's basically all that little like PCB did was do that and break it out to a test clip. I'll try to see if I have any more of those left. And like I said, I'd like to try to open source it. There's a few things I actually have to reach out to about that, because I decided to build that because I was building it for myself personally. Because I wired this once to a breadboard and went, wow, that's a hassle. That needs to be I need something to just streamline that a bit. I don't want to mess with all this wiring every time I want to dump an SPI flash chip. So I created that board. Problem with that is I designed it and I was following the design guidelines that Flipper has for their design. And there's two fonts that are used in that are like, they have licensing where you have to credit to them and also potentially ask for royalties. If you have a commercial product with it, I would have to look into what I would have to do to actually open source it if I keep those in there, or I would have to remove those and change the look and feel of the board a bit to get rid of those. But I'll take a look at that and see what I can do. Overall, it's actually not a hard one to do, and this also might be a good project as well. I don't know if you've ever used a tool called KiCad. It's actually like an electronic design CAD software, but there's a channel on YouTube that has a Getting to Blinky tutorial that kind of walks you through the entire process of designing PCB, like designing the schematic, creating the footprints, and designing the PCB, sending it off to a mill, generating your BOM, getting the materials in, and then assembling and testing your board. I highly recommend running through that tutorial if you can, because that would actually teach you the process of manufacturing and creating PCBs yourself. And this would actually be a good project to start with, because you're just doing a wiring schematic, really. So we can do that as well. But if I can't get that open sourced, just send an email. We have a contact us form on the thing. I'll see if I have any more, and if I do, I'll just ship you one.